Here's what we got first off. Samsung dryer here. As usual, taken from an appliantology topic. So the issue here is that the motor would run, you'd start a cycle, the motor would run for about 10 seconds and then kick off. I think we can all tell what's happening there. I mean, anyone know what's happening there, why the motor's kicking off after 10 seconds?
The high
Any
limit
guesses?
thermostat, the
That that
little
that
black,
that's
right?
built into the motor. You talking about the one built into the motor, Joe?
No, the one that's on the front of the blower motor.
Well, if that were to go, I don't think you'd see that happen repeatedly 10 seconds into the cycle.
I
It,
had
ten,
one go where it took like 3 minutes for it to fail. So that's why I thought it.
Yeah,
Interesting, yeah.
but that's a good thought, but it takes a little bit. They're a little slower reacting.
Mm.
But Sam, we've got there's another thermostat built into the motor. Sam will show you
Oh.
that one.
Yeah, right here. You got the thermal protector that's actually built into the motor itself.
Hmm.
By
You
the way,
guys know,
this is not unique. Sorry, Sam, I didn't mean to
yeah,
overtalk you, but
no, go for it.
this is not unique. That Sam circled that little limit inside the motor there. That's not unique to dryers. All of your AC, asynchronous split phase motors will have an internal thermal protector built into the motor. It's just how all these AC motors are made. And so that's always there. Compressors have them, everybody has them. Go ahead, Sam.
Yeah, so the way you can tell it's internal, by the way, is I'm sure you're all familiar with the schematic convention of if you've got a box around something, that means it's all one component. It's all one part, right? So you've got the motor windings in here, but you've also got the thermal protector and you have the centrifugal switches, and those are all boxed in as part of the motor.
Sam, for just a second, blow that box up a little bit. Just zoom in on that. So yeah, there we go.
Yeah. Some schematics will do it as a solid line, like it is here. Some will do a dashed line, but generally that's just what that means. If you see a box around something, it means they're showing one discrete component. So if the centrifugal switch fails or the thermal protector fails, then it means you're replacing a motor. You're not going to be going in and replacing just a centrifugal switch.
Yeah, I think some of the older dryers you could replace the centrifugal switch separately, but that's not the case here. And then the newer dryers.
So when you have back to our problem at hand now that we've kind of covered what's going on here in this motor, when you have this problem of motor runs for, 10, 15 seconds, whatever it is, and then kicks out, you know that what's kicking it out is that thermal protector. Um, what is a quick, easy electrical measurement you can do to figure out what's happening here, or to just take a health reading on the
To
motor?
verify that the motor or not to just either uh, include or exclude that the motor's internal thermal overload is kicking out. First of all, does everybody understand why that internal protector is there in all motors? And it's precisely to protect against an overheat situation. So you don't burn up the windings and you know you've got some protection for the motor in case of, and what makes heat? What generates heat in a motor?
Friction, no. Upper
Electricity.
road.
Uh,
Block rotor.
but what electrical quantity generates heat inside a motor?
Ants.
Amps. You got it. So if go ahead, Sam, you take it from there.
Yeah, so amps is what you'd want to measure because uh, what how would the amps present in a case where you have a locked up, let's say, okay, I heard locked rotor get thrown out there. So in a locked rotor situation, would you expect the amps to be higher or lower than the specification?
Higher.
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 Right.
Right. And so more amps, more heat. And
Because it's
it's that
always
heat.
amps that makes heat in electrical circuits. Volts just create in a complete circuit, volts just create the condition for electrons to start zipping. And those electrons, when they move, that creates heat.
Because heat is a kind of it's energy, it's a kind of power output uh from the circuit, and that can be intentional in the case of like a heating element, or it can be just a side effect or a byproduct in a lot of other circuits where, the intention of a motor in an ideal world, a motor would run totally cool at room temperature. It wouldn't produce any excess heat. All the electrical energy would be converted into the motor spinning. But we don't live in an ideal world, so even when the motor is running properly, you still have some heat being generated by the amps blasting through the motor coils.
Yeah, these electric motors, just fun fact to know and tell, they're only about 60% efficient. So, a lot of or a good chunk of the energy, not most of it, but a good chunk of it, that you put into the motor to make it do its work gets wasted as heat instead of going to actually spin the rotor, which is the intended function of the electrical power input. To convert, you want as much of that you're inputting electrical power into the motor. The ideal in an ideal world, 100% of that would be converted into mechanical power, the spinning shaft. But that we've always got losses. Anytime you convert energy from one form to another, you've got losses. So you're putting electrical power into a motor, getting mechanical power out, but you get a lot of losses, and that shows up as heat.
So you want to do your amp measurement to verify that it's the thermal protector that's kicking out the motor. Where would you do that? Where would you put your amp clamp on the schematic? Where would you put it?
But Sam, just before we go there, I just want everybody to make sure that you understand this concept of you've got this motor, it's kicking out soon, so you've got some fast acting component. It's got to be the local one inside the motor here, the thermal overload protector. Your mind should immediately be thinking, I need to get an amp measurement on that
Yeah.
motor.
Mm-hmm.
So where is a good EEPS for doing that? And EEPS are all about convenience for the tech.
Black
Save
wire.
us time. Sorry, go ahead.
I heard the black wire. Which black wire are you talking about?
Oh, well, I see a better one now. It's the brown wire, number 4.
Yes,
Right
number
there.
4 here, but
Yeah, number 6 is a black wire.
right. Okay.
On the board, 5-1 there, where brown connects in.
There
Ding,
we
ding,
go.
ding.
That's the place.
That's
Yeah.
the convenient EEPS that we want it because it's easy to get to. We don't have to disassemble the beast and get down into the belly and get it right on the motor. We've got
Right.
a line going right up to the control board. 2 screws, flip it down, take an amp measurement.
Yep. Just put your
Yeah, right there.
you just put your meter, right around there. There you go. Take your amp measurement.
Yeah.
And where would you find the spec that you're trying to compare it to?
Right, because it doesn't make any sense to do an electrical measurement unless you have a spec to compare it with. So obviously we need a
This is
spec.
Samsung, so it'd be fast track, wherever you get that fast track for Samsung.
If they give it to you there, which
They
they
don't in
may
this
or may
one.
not sometimes,
They
but
often don't give us that on the fast track. Wish they did. That would be awesome. But that
Mm-hmm.
doesn't stop us. There are other ways of skinning this cat.
there's always going to be
Nameplate.
an amperage spec, yeah, on the nameplate of the motor.
Yeah.
And now this doesn't mean you have to disassemble and actually get eyeballs on that nameplate. As you can see from the little arrows here, this is a screenshot we took from the web. So you can just search for your part number for the motor and find a picture of the nameplate.
Yeah, go to an online parts site, repair clinic, appliance parts pro, whatever you
Mhm.
like that has nice pictures, and look up the part number for your motor and look at the nameplate.
So there's our amperage spec.
That's the
Question
full load
about
amps.
this amperage spec. Well, yeah, is that the amps that you'd expect to see under normal operation, 5.3 amps?
Yeah.
Yes.
Yes.
Is it? Because it seems kind of high. What this is
Wait.
actually is the full load amps. This is like
Oh.
the upper threshold. You should probably never see this during normal operation. This is if the motor's at like doing the maximum amount of work it possibly can. Is going to be at 5.3 amps.
So
Right,
when
so-
it's running at that 1630 RPM, you should theoretically see somewhere in the ballpark of 5.3.
Yeah, generally a little bit less, maybe,
Mhm.
unless it's really, but what their full load amps is different from lock rotor. Lock
Mhm.
rotor amps is where the rotor, you've actually got it clamped in a vise to keep it from
Mhm.
moving, and you're applying power to the motor. So you've
Mhm.
got volts and you got amps going through, and it's going to be something a lot higher actually than
Mhm.
5.3 amps. So as the your amps will go up as the motor gets loaded, as it's turning a bigger, the shaft is having to apply more torque. Your amps will go up. And finally, to lock rotor current, where it'll be something, they don't give us lock rotor current on this one. It's always full load amps that you're given there. And you're looking for something uh, no greater than full load amps when
Yeah.
when the dryer's spinning a drum.
So
So,
you do your, oh, go on.
the 5.3 amp, we can assume that if it's the drum full of clothes, it will get up to 5 amp.
Yeah.
Assume.
Yeah,
Yep.
somewhere close to that. Yeah.
Yep. That's a good ballpark. That's a good technical ballpark working estimate.
So if you take your amp measurement and you get something higher than 5.3, how do you determine if that's because of a failure of the motor itself or one of the motor's internal components? How do you tell if it's a failure of that or um, just, something that's locking up the motor? What's a way to kind of half split that?
Because just to backfill Sam's question, you can also induce restrictions on the motor's rotor, um,
Mm.
its torque requirements by having, for example, seized up drum bearings, and so the motor's having to spin a drum, but the drum bearings, the rollers aren't spinning. That's going to put a lot more torque requirement on the motor.
Yep.
Yes.
So,
I mean, you could just manually spin the drum, right? Like
well,
if
yeah,
the
to tell
belt is
that.
there, then
Yeah.
yeah.
That's a way to feel if you are getting excess resistance there.
And that's totally legit. That's a good,
Yeah.
valid troubleshooting move.
If you want to get an eye on the amps, like you're still doing, you still got your amp clamp on that wire. A good thing you can do is just unhook the belt, take the belt
Hmm.
off of the motor,
Mm.
and then if you run the motor, if you still get excessive amperage, you know that there's a problem with the motor. There's no other option. The
It
motor has
could be
no,
bad bearings that the
yeah.
rotor is spinning on, the internal bearings in the motor. Those could be shot. There's lots of different things that can go on inside the motor itself that can cause excessive amps.
So like at
Th-
this point, the initial amp reading is okay, well, now I have to disassemble to see what is happening.
Right. To go down and unhook the belt, then you will have to
Hmm.
disassemble.
Yeah.
Does it have a belt switch on that one? I didn't see.
Yeah, there is.
Yes.
So then if we unhook the belt, we would just have to hold
You'll have
the
to,
switch closed.
right. Just jump that out.
Yeah.
Yep. You just put a
And,
jumper across here.
and then that internal shutoff, how quick before that resets itself?
Did you get the seminar?
I don't have a spec on that.
It's a few minutes. It just has to
Yeah.
Is
cool
it?
down. So the
It's
motor
just,
has to
yeah.
dissipate enough heat to cool down that bimetal that's built into it. That thermal overload inside the motor, that is a bimetal. And so it'll have to cool down to some amount. And generally it takes a few minutes in general,
Yep.
is my experience.
So by just turning it on, it shutting itself down and waiting and turning it on, there's nothing else in that circuit that is going to reset itself, correct?
Not external to the motor. The only other thing in that circuit, well, you've got that's a thermal cutoff. They're showing that
Yeah.
as a thermal fuse looking thing. If that opens, it doesn't reset.
Right.
So it's just the internal thermal overload inside the motor that will reset.
So using just some general knowledge on that, you could come to a conclusion also.
Right.
Just a quick question. Assuming that, let's say that the dryer cannot pull enough air, let's say the blower is full of lint and it kind of starving, it's not pulling enough air. Can that affect that bimetal in terms of opening up that bimetal? Because due to excess heat in the dryer, it's not getting enough air to kind of circulate in the motor area.
Yeah, no.
Okay.
Generally, no. That's going to affect your thermal cutoff
Yeah.
Okay. Yeah.
because that's on the
You're
blower housing.
exactly.
You're not gonna be moving enough air through the blower housing to keep that cutoff from opening.
The amount of heat buildup you would have would far exceed the cutoff for this fuse before you got to the point of tripping the thermal protector.
They do show another thermal cutoff over on the left. I'm not sure which one is played, but the airflow through the dryer itself is going to affect one of your thermal cutoffs,
Yeah.
possibly the high limit. Now your
Okay.
thermal cutoff 3 and your high limit, those are resettable. They're showing those as resettable bimetals. The
Yep.
thermal cutoff that's in the motor circuit, TH1, that's not resettable. That's a thermal fuse.
Exactly.
Mhm.
Could you show us how you distinguish those, please?
Oh, yeah, that's a great point. I was about to show that. This little square squiggle here, that's the symbol for a bimetal.
Okay.
So any of these switches that have that little square bit there,
With the smiley face. So the smiley face, the
yeah,
little half circle there with the squiggle, the square squiggle attached to it, that's indicating a bimetal, a thermally activated and self-resetting bimetal.
yeah,
Yeah.
Compare that to TH1, the thermal cutoff, and they show it as just a wavy line. That's
Yep.
like typical of a fuse, because that's what it is, a thermal fuse. Once it's open, it's done. You got to replace it.
Okay. And the resettable, is that with the little angle at the end of the curve? On
Yeah.
The resettable ones are TH3, TH2, and the motor's internal thermal protection, T/P,
Yeah.
they call it
That's
out
to
as.
represent a spring.
Okay.
Well, they're not. Everybody know what a bimetal is? So
Yeah.
you got this little thing of metal, and you got two dissimilar metals bonded together. They expand and contract at different rates, and they can set that according to what temperature they
Oh,
want it to open
yeah.
and then reclose at.
yeah,
So they're just showing you with the squiggle that it's a thermally actuated bimetal, and that's what the little half circle indicates, that it's just and
Yeah.
they pop open and pop closed.
yeah. I think what it's actually kind of representing there is that you have the bimetals closed until you reach a certain temperature threshold. So close, then suddenly it goes open, and then after a while it cools down enough, and then it goes closed again.
Yeah, and
That's
they
kind of what
snap
that.
open. Anybody
Yeah.
ever remember Edmund Scientific when you were a kid, if you got those little kits? Yeah.
Yeah.
Yep. And one of the kits that they gave you was little bimetals. So you'd close them and then then you could let it cool off, and then they would actually snap the other way and hop off the table.
Yeah.
That's what these are. They're little bimetals, but they don't hop around because they're in a housing. But they make and break those electrical contacts.
So the smiley face makes it a resettable? Is that?
Yeah, that's just it's showing the flexing in a stylized way, the flexing of the bimetal, because that's what the bimetal physically flexes. It'll flex concave or convex.
Yeah.
So,
All right.
okay.
So sorry if I didn't mean to cut you off. If you had another clarifying question there.
Well, I'm a little confused, pardon me, but on TH3 and TH2 is a different symbol than
TH1.
right.
Yep.
And so the smiley, and what I heard was the TH3 and TH2 are resettable.
Yep, they're resettable bimetals.
And what distinguishes them because of the smiley face?
Well, and on the schematic, but they're physically distinguished too. Oh, in fact, we have Sam, I don't know if you let me see if I can get that real quick. We have a let me just grab that link real quick. We've got a whole other webinar that you guys might want to watch on dryer thermal controls. Here we go. I'm just going to put this in the chat box and you guys can watch it later. It explains in more detail the distinction between these thermal fuses, thermal cutoffs, and high limits. And let me get into chat here to everyone. There you go.
Okay. Thanks.
So that goes into detail about dryer thermal controls. And TH3, somebody's asking in chat, Rudy is on TH3. Generally non-resettable. I'm not sure about the general case. In this case, they're showing it as resettable. And Tim is, what is the symbol for a fuse that resets itself versus a push button reset.
A fuse won't
Um,
reset itself.
Sorry, Farley?
A fuse won't reset itself. That's one thing that's different. A fuse is a fuse. It's once it's gone, it's gone.
That's right.
Okay. Okay.
Yep. So, Tim, does that answer your question?
All right.
Um,
So
if not, just let us know.
we've gone over all the
Oh, Tim says no, that didn't answer his question. So, Tim,
uh,
there are, we don't have one here. In this case, they're not showing it as manually resettable. I know in some of the ASCOs, some of the Bosches, they'll actually have a resettable. Um, and they play fast and loose with these names. Thermal cutoffs can be shown as a fuse like
Yeah.
TH1 or as a bimetal like TH3. They're calling them both thermal cutoffs because of the function they serve. So you got to we're kind of at the mercy of how they draw the symbols. They are not showing TH1 as resettable. But some of them they do. Some of the ASCOs and Bosches, and there'll be a little button symbol they may not even show it at all. You just have to look at or know it from the service manual or from taking it apart and looking or seeing there's a little red button. Decor ovens will have a resettable bimetal where you can press the red button and get it going again.
Yeah, a lot of G dishwashers have that TCO underneath the actual or the bottom that is resettable as well.
Yeah. Yeah. So in the case of this Samsung dryer, and we're kind of at the mercy of what they're giving us here, and also just from knowing from working on these dryers. The TH1 is a thermal fuse, which they're calling a cutoff, which is fine. But there's no reset to this one. They're not calling out any type of reset. Once it's open, that's it. You got to replace it. Rudy Valenta said, "Show Carl the non-resettable symbol." Well, the TH1 is shown as a non-resettable thermal fuse. But we
Yeah.
don't have any bimetals that are shown as resettable because they automatically reset. In fact, you'll see stamped on the side of the bimetals itself, you'll see it's cut out and cut in temperatures stamped right on it.
Yeah.
In the case of Samsung, they're given in centigrade, so you got to watch out for that. If you're concerned about correlating with temperature, you got to convert to Fahrenheit.
So
did we get Tim got confused between bimetal versus, okay. All right, good.
we got it
Good,
now.
Tim. All right.
That was a good little discourse on the thermal controls.
The main thing that I wanted people to get out of this one is that when you have a motor, any motor anywhere, I'm talking AC motors now, just in the realm of AC, asynchronous split phase motors, which is what this is, what's in dryers, what's in washers, what's in compressors. Anytime you have one of those and it runs for a few seconds and then kicks out, you should immediately be thinking it's internal thermal protection. And your go-to measurement for that is amps, because it's only amps that can make that thing open. Volts don't affect anything. All they do is push the electrons through the circuit.
Yep. And
Got
then
to
you
have
can
volts to have amps, but it's amps that actually do the work and make things happen in a circuit.
and then you can isolate the motor by disconnecting the belts to see if it's a problem that's being induced upon the motor by another issue or if it's a problem with the motor itself. I think the last thing I wanted to cover with this example is I'll pose the question. Does everyone here know why is it that you get higher amps when the motor is locked up? Why is it that you get those really high locked rotor amps? What is it that makes the amps higher?
It's trying to do more work than it should.
Well, but is the motor like sucking up more amps to try to get more work done? Is that how loads work electrically?
Well, it's trying to get up to the starting speed, and it can't achieve that for some reason.
Mhm.
Yeah, but we talk about current draw and how many amps is this load drawing, for example.
Mhm.
Loads don't actually suck amps. So it's okay to use that term as long as you know in your head what's really going on. It's volts that push amps, and the only thing that slows amps down is ohms. And you can have ohms from two sources. Go ahead, Sam.
Yeah, you can have, well, I think Rudy just posted something in chat. He said resistance increase. But I want to pose this to you, Rudy. If the resistance goes up in a circuit, what does that mean about the amperage? Will the amperage go up or will it go down?
Go down.
It would go
Yeah,
down. So
that's
so
Ohm's
the
law.
resistance is not going, yes, exactly. Ohm's law. That's what tells us that. So if we had more resistance in the circuit, if we had more electrical resistance, right? And we have to, I'm saying that to distinguish from physical resistance, the physical resistance that can be put on the motor by a locked up drum. Um,
For sure. Huh.
More electrical resistance will result in less amperage. So that's clearly not what's going on here. In fact, what we know has to be going on here is somehow we have less resistance
All right.
when we have locked rotor in a motor.
Hmm.
So we have less electrical resistance when the motor is locked up. And the reason for that is because you have two different kinds of resistance, though really there's different terms that are used for them. There's resistance and there's reactance.
They're both
Uh,
ohms,
yeah.
but they're in different phases, different planes, so that you can't add them together directly. You have to add them together vectorially,
And we
which
don't
we don't
need
get
to
into that. But we just, as
exactly.
techs, we need to be aware that this is what's going on. Go ahead, Sam.
We
Sorry.
don't need to understand exactly how reactance works. It's just not important for us, but we do need to be aware that it exists, especially for understanding motors. Um, so when the motor is spinning, it's, you're generating an electromagnetic field and that produces reactance. You're getting extra ohms that are present while the motor is spinning.
But
Uh,
these are ohms that you cannot measure with your meter. Your meter only
Correct.
measures real resistance in a dead circuit. When there's amps flowing through, there's a different type of ohms that, magically appears due to electromagnetics and all this type of thing that creates its own ohms when electrons are moving. Your meter cannot measure that, but it is real. Actually, it's imaginary. In mathematically speaking,
Mathematically imaginary, but
yeah,
yes.
but it's real in terms of the real world effects. Um,
This is why if you've ever tried to, just out of curiosity, use Ohm's law to calculate like what the power output of a motor should be based off the resistance of its windings, you get numbers that don't correlate with the actual power spec on that motor. And that's because the power spec of that motor is calculated using the total impedance of that motor, including both the resistance of the windings and the reactance while it's spinning.
right. So all your meter can measure is the copper resistance of the winding. Your meter cannot measure the electromagnetic resistance called inductive reactance in the case of a motor. Your meter can't measure that.
So all,
That's why
oh,
amps are your go-to story because watts are the bottom line for any AC load. And amps are a direct proxy for watts. Because if you know amps and you know volts, you know watts. Everybody get that? P equals I times E. So it's just basic Ohm's law in everybody's favorite equation. Sam Tim has a question in chat.
okay. Had a GE washer motor yesterday running very loud. I did not think to check amps, but the motor got extremely hot. This discussion is enlightening. I ordered a new motor just on the sound and heat felt. This now gives me another confirmation. That's great.
Very good. And just whenever you got a heat issue like what Tim just described in chat, the only thing that can make heat internally is amps. And so that your first thing would be to check amps and compare to spec. And that's dead proof that you have a defective or not defective, as the case may be, motor.
So all this is to say, right, all this talk about reactance and impedance, right? It's not to boggle your mind. It's just something for you to be aware of, to know that you have fewer ohms present when the motor is running, when it's properly running and spinning. You actually have, sorry, other way around. You have more ohms when the motor
Right.
is
Right.
running.
Now you've got the copper ohms and the reactance ohms.
Yes. When the motor is locked up, then you have less ohms because you only have the ohms of the copper windings. You
That's
don't
why
have any of
current
that
goes so
reactance.
so high. When you have locked rotor, that's why the current is so much higher because you no longer have the reactive component. You no longer have the inductive reactance that's opposing the movement of electrons. All you
Correct.
have is the resistance of the copper winding, the copper itself that's in the windings.
And the only work that those amps are doing is just they're just being dropped across. You just have voltage being dropped across those windings, and you're just shedding heat. You're just
Yeah.
converting electrical energy into thermal energy across those coils.
Yeah.
So that's
This is why you hear me um, push back against a lot of these guys who depend on ohms because it's not the full story and it can be very misleading. So whenever you can, rely on volts and amps instead of ohms.
So we're touching on the realm of physics here rather than the real world. I mean, that we
Well, that's
can
what we do. That's as
specify, right?
technicians, it's all about applied physics.
Yeah, yeah. That makes it in the theoretical end, then we can only see those ohms mathematically.
That's right.
Oh,
We can't measure it with our meter.
okay.
You can see it. You'll see it in show up in amps
I'm
on your
sure.
meter, but you won't see it show up in ohms on your meter.
Okay. That's what I thought you were saying.
Yep. Yep. Good question.
Oh,
So, yeah, does that make sense to everyone? I know it can be kind of, you can get into the weeds with this reactance impedance stuff, but it's
You just need to
important
be
to
aware,
be
as
aware of.
techs, we just need to be aware that that's a thing. Anytime you're dealing with any type of inductive load, like a motor's a big inductor with the secondary winding put on bearings instead of, bolted into the same frame as a transformer. That's basically what a motor is. A motor is a transformer, but the secondary is not bolted down. Instead, it's put on bearings so it can spin, and it's pushed around by electromagnetism. It's kind of amazing.
Hmm.
That's a Tesla thing. Did you know that AC motors came out of, it was one of the things that Nikola Tesla
Yeah,
invented.
not Elon Musk's Tesla, the original
No,
Tesla.
yeah, that's right. That's not nothing to do with Elon Musk, but this is the real Tesla.
so you mentioned impedance.
Mhm.
Is that the same as reactance then?
Good question. Yeah, so impedance is the term uh, for both resistance and reactance put together. So it's like the umbrella term for both of those.
Right. And then reactance can, not to, I hope this doesn't confuse everybody further, but reactance, you can have inductive, which is the most common form that we see, or capacitive reactance. Both inductors and capacitors are reactive components, and they generate their own opposition to current flow. So, and you don't have to know the math of this. It gets into the imaginary plane and all that stuff. Don't worry about that. You just need to know that reactance is a real thing or imaginary thing in uh, in um, in motors that we deal with.
Yep. And so that's why you have fewer ohms when the motor's at standstill or
Yeah, and
stuck at standstill.
fun fact to know and tell, reactance is all on the imaginary plane, the mathematical imaginary plane. So that's why I'm sometimes my joke is, it's not real, but it's imaginary, but it is real because in its physical effects.
If you can imagine it, it will be there.
Yep.
All right. Well, that's it on this one.